Right, so this is IMF for intermolecular forces. Okay, what's one intermolecular force that we talked about in class? It's the strongest one. Okay, ionic, very good. Okay, so this is a full charge transfer. Okay, so this will be the strongest. Okay, this is a metal with a non-metal, a metal with a non-metal. And it's a full electron transfer, or a full 2-electron transfer. You give electrons, someone gives it, another person takes it. All right. The next one, what's the next strongest one? Okay, both of these are polar. Both of these are polar. Polar. Okay. But out of that polar, one is a little bit stronger than the other. What is that one? Very good. This is called hydrogen bonding. Okay. And this is a partial, not a full charge, full positive, full negative. This is partial positive with partial negative. Okay, this is also called dipole-dipole. Okay, and then what's the other one called? Okay, it's also called dipole-dipole. It's the same thing, but this is a little bit stronger. Okay, a little bit stronger polar than normal dipole-dipole. All right, and then, so ionic is the strongest. We have hydrogen bonding. We have dipole-dipole. This is partial. Okay, partial positive with a partial negative. This here, IMF, is a full positive with a full negative. All right, this is a full positive with a full negative. This is ion dipole force. Okay, so I don't know if it's strong. I mean, it's probably around here. Okay, I'll just circle it because it's not really... it's strong, but I don't know the ranking. Okay, it's just strong. So don't worry about the ranking here. Just keep it. Okay, but ionic would be the strongest. And this is a full charge with a partial charge. Okay, so there's something called solvation or hydration. Okay, so this is a partial negative with a partial positive, dipole-dipole. This is a full positive or full negative with a partial positive, partial negative. The full charge comes from the ion, correct? Where does the partial come from? Where does the partial charge come from? It comes from the dipole. All right, so let's go to page 4 and talk more about this. All right, so ion dipole forces. As an example, let's talk about solvation. Okay, everyone knows sodium chloride, maybe, perhaps, salt. Okay, so sodium chloride is an ionic compound. Okay, it's an ionic compound, and we talked a little bit last time about how it's a lattice, and it's a very strong in IMF by virtue of it being ionic. But what we can do is take some of this solid sodium chloride, like you do when you cook in the kitchen, and dissolve it in water. Okay, what happens when you dissolve it in water? Okay, this is polar covalent, and it can hydrogen bond. But when we dissolve it, what happens is a phenomenon known as solvation or hydration. You heard of hydration? Okay, maybe if you drink Gatorade or one of these drinks, they talk a lot about hydration, okay, or solvation. And literally the water, again, water is this amazing substance I'd like to try to convince you. It actually can break this lattice. It can actually disrupt this ionic intermolecular force. How does it do that? It creates a solvation shell. So if we take sodium chloride and put it in water, the water breaks this it separates the charges. So you'll have like Na plus here, and you'll have Cl minus there. Okay, and water forms a shell. So what does this positive charge interact with? Negative. So it will interact with the partial negative of water. This is the full positive charge. Okay, and water just, surrounds it. And kind of like what we see here. You see this? Okay, here's the water forming a shell around the cation, and water will do the same thing, forming a shell around the anion. Okay, what will this full negative interact with? Positive. Okay, partial positive. So there's that full negative interacting with the partial positives of the water shell. Okay, water's literally surrounding the ion, and here's the full positive interacting with the partial negative of the water. Water's literally surrounding it like a shell. Okay, so this is called solvation. You kind of see that here. So this is an ion dipole force. All right, full charge, partial charge. We will contrast that with dipole-dipole, which is partial. We'll contrast that with dipole-dipole polar, which is partial charge interacting with a partial charge. An ion dipole is a full charge interacting with a partial charge. Example is hydration and solvation, or solvation. So anybody have any comments or questions on this? Solvation, hydration, it's an ion dipole force. Okay, an ion dipole force. All right, our last intermolecular force. Yes?
Can it be considered intramolecular forces?
Ionic intramolecular forces? I don't think so. That's like sp2, sp3. Those are hybridizations. Yeah, so I would not call it an intramolecular force. Ionic. Yeah, I would not call that ionic. I would call none of these intra. They're all inter. Okay, sp2, sp3, sp hybridizations. That's intramolecular forces. Okay, orbitals hybridizing together to form the molecule. All right, let's go over our last intermolecular forces, and that is dispersion forces. So what I want you guys to know about dispersion forces is that it is the weakest. Okay, it is the weakest IMF. The weakest intermolecular force. Okay, it is created by a temporary induced dipole. Temporary induced dipole caused by the electron clouds circulating. You know, electron clouds move around just like clouds move around here in our atmosphere. Electron clouds will move around the atom, okay, and induce a very, very temporary, very weak dipole. It's very weak. Okay, it's very temporary and very fleeting. By virtue of it being very temporary and very fleeting intermolecular force, it makes it weak. Because as the electron cloud circulates, it induces on the neighbor molecule a little bit of a dipole, and then it comes here a little bit of a dipole as the electron cloud circulates. Okay, but it's very, very an insignificant, weak intermolecular force, as I mentioned before. So with dispersion forces, we're looking at molecules that are not polar, but are nonpolar. Okay? So what does nonpolar mean? Okay? If polar means it has a partial positive and a partial negative within the molecule, what would nonpolar mean? What would nonpolar be? Negative charges? Why negative? No charge. Okay, it would have no net dipole moment. Okay, no net dipole moment. Okay, what would polar molecules have? Okay, polar molecules will have a dipole moment. But what will nonpolar molecules have? None. Okay, none. No net dipole moment. Okay, and what type of IMF would be those nonpolar molecules? What would be dispersion? This is also known as van der Waals. Okay, van der Waals forces. So let me give you an example of a functional group that is dispersion. Okay, that is dispersion. Okay. All right, so here we have another functional group that I'd like for you to learn. And they're on this sheet, which I'll give you at the end of the class, which you can use on the exam. But if you take, higher level chemistry classes, it's good to know them and have them memorized. Okay, so we have alcohols, which are this. We have ethers, which are this. And then we have alcohols as a functional group, which is this. We have ethers as a functional group. Which is this. Okay. Another functional group I'd like for you guys to know are the alkanes. Okay, how many of you have heard this term before, alkanes? Maybe you can raise your hand. Alkanes. Have you heard of alkanes? You have, alkaline? Susanna? Huh? Alkaline? Not alkaline. Alkaline is something else. How many of you have heard of alkanes? How many of you have heard of alcohols? Okay, how many of you have heard of ethers? Okay. And how many of you have heard of alkanes? Okay, you may not have heard of alkanes, but have you heard of methane? Okay, that's one carbon. Okay, what would two carbons be? Ethane. Okay, what would three carbons be? Propane. Okay, what would four carbons be? Butane. Okay, what would five carbons be? Pentane. Okay, hold on. What would six carbons be? Hexane, 7 carbons, septane, 8 carbons, octane, 9 carbons, nonane, 10 carbons, decane. Okay, so are these molecules polar or nonpolar? What would this be? Be polar or non-polar? Do you see any electronegative atoms here? Okay, there's no pulling power. Hydrogen cannot pull. Carbon is not electronegative. Okay, electronegative, you're looking at the oxygens and halogens. Okay, maybe a little bit nitrogen. Pull. Okay, this is not a good vacuum cleaner in sucking and taking in electron density. So this is non-polar. What would be the IMF for this? Dispersion. Okay, dispersion. Do you guys see any partial positive charge or partial negative charge here? No. Okay, no partial negative, no partial positive, no net dipole moment. It's not polar. In fact, it's the opposite. It's the very opposite, and it's called nonpolar. Okay? And you can see here, again, dispersion. Just remember, okay, just remember that it's a temporary weak force. Okay, we see dispersion forces with the hydrocarbons. Okay, and we see it with some other nonpolar molecules as well. Okay, we're looking at something that is induced, excuse me. And it's a temporary dipole. It's not a permanent dipole. Okay? Because it's temporary, as the electron clouds moves around the molecule, you don't get any juice. Okay? It just comes and goes. It comes and goes like a passing cloud. It makes it a very weak IMF. Right? What would be the IMF for this molecule here? This is called carbon tetrachloride. What do you guys think the Lewis structure? I'm sorry, not the Lewis structure. What do you guys? This is the Lewis structure. What do you guys think the IMF would be for this molecule? It's called carbon tetrachloride. The chlorine is electronegative. It's a halogen, and they pull. All those halogens, chlorine, fluorine, bromine, they pull on this. So do you think this would be polar or non-polar? What do you guys think? Polar? Okay. So this chlorine pulls this way. What will that chlorine do? Pull the other way. Okay. Okay, what will this chlorine do up top? Okay, it pulls. What about this chlorine at the bottom? Pulls down. Right. So now my question to you, is this polar or non-polar still?
Zero.
It's going to be non-polar. Very good, Sam, right? Why is it non-polar? Wait, say it again? Yes, this up is canceled out by what? This down. What is this left pull canceled out by? Right, the right pull. So this vector cancels out that vector. This top vector cancels out that bottom vector. So is this polar or non-polar? It's non-polar, even though you have electronegative chlorine atoms. Because the molecule is symmetric, it is non-polar. Because it is symmetric and they cancel out each other, these dipoles, they cancel out. Literally, they're canceling each other out. It's non-polar. So what would the IMF for this be? Dispersion. Very good. Okay, this too would be dispersion. Okay, this also would be dispersion. All right, let's go back to the very first page of our notes here. okay, where we have this table on page 1. Coming back here, okay, why does ethanol have a higher boiling point than this ether? This is called an alcohol, and the name of this specific alcohol is called ethanol. This is an ether. The name of this specific ether is dimethyl ether. Why would this ethanol, if they have the same formula, have a higher boiling point than this dimethyl ether? It's the same number of carbons, hydrogens, and oxygen. Why is this have such a higher boiling point? 78 degrees versus minus 24 degrees. Right, a hydrogen bond. Okay? And why would this be so lower, even though it's both polar? Even though they're both polar, this does not have hydrogen bonding. Okay, let's add sodium chloride to this. Okay, where would you rank sodium chloride in this? Higher or lower? Or somewhere in the middle? Higher. Higher than which one? In fact, because it's ionic, it would be the highest. Okay, so we don't know the boiling point, and don't use your phone to figure it out. Okay, we can just know that it's going to be the highest, because why? Why will it be the highest boiling point? Because it's ionic. Okay, because it's ionic. Very good. How about this? How about we put ethane, or no, propane. We'll do propane. Okay, where would protein be? Protein. Where would propane be? Where would propane be here? Would it be the highest, or the lowest, or somewhere in the middle? Where would it be? The lowest. Why would it be the lowest boiling point? Casey, right? Sorry? You're right. It's not because it's nonpolar, but what else? And it's nonpolar because of dispersion. Okay, so both are right answers, but I think the correct answer, more correct answer, is dispersion. Okay. So you do know. All right. So which would have the lowest boiling point? Propane. This is called propane. Okay, which would have the highest boiling point? The ionic compound. Which would have kind of the second, or kind of high. The one that's polar but can hydrogen bond, and the one that's just polar would be kind of, I don't know, kind of in the middle. All right. So let's summarize this. Okay, on the next page. Alright, so if we're looking at the IMF, the strongest would be ionic. Okay, then we have hydrogen bonding. And then we have dipole-dipole. And then we have dispersion. Okay, which is the strongest? Okay, which is the weakest? Okay, if we were to rank the boiling points, which would have the highest boiling point? Which would have the highest boiling point? Okay, the one that is held together by ionic bonds, good. And which would have the lowest? Okay, this would have the lowest boiling point. Okay. What do we associate dispersion with? What type of molecule? Nonpolar. And in terms of hydrogen bonding and dipole-dipole, what are they both constitute? They're both polar, but which one is stronger? Okay, of the polar, hydrogen bonding is stronger. What do we look for when we say a molecule is polar? What three things? Okay, we're looking at, I think I hear it, or I heard it. Okay, anywhere in the molecule there's an OH. What else? Okay, and a fluorine. Okay. Then there could be the potential for hydrogen bonding. Okay. Fluorine, OH, and NH. As an example, let's take a look at this table. You do not have to know this, but this is what they use in organic chemistry. This point and these points represent a carbon with hydrogens. Okay, so you'll learn this in organics, so you don't need this for my class. This is a carbon filled with hydrogens. This is a carbon, carbon, carbon bound to an NH2. Here's a nitrogen bound to a carbon with H's, so that would be a CH3. Here's a carbon with hydrogens, carbon with a hydrogen, carbon with a hydrogen. So those little points represent a carbon. But look at the boiling point here. Okay, why do you think the boiling point of tetramethyl ammonium chloride is so high, greater than 260 degrees? Okay, it's ionic. Here's the positive charge, here's the minus charge. Okay, why do you think this is 77 degrees? Okay, what do we look for? Okay, the hydrogen bond is caused by the NH. Right, same thing here. Okay, you see the full negative, full positive, okay, greater than 260 degrees. Ionic. This is ionic. Okay, where's the hydrogen bond coming from here? The OH. Okay. Why is this polar? Okay, this is a carbon, double bond oxygen, this is a carbon, this is a carbon. So we have an oxygen pulling this way, we have that double bond oxygen pulling that way, pulling up, so that's going to be partial negative. This oxygen is partial negative. Okay, we have the oxygen pulling the other way, so it's polar, but it's not hydrogen bonding because there's no OH. There's no NH, and there's no fluorine in the molecule. Right, so polar, but this is polar, and can hydrogen bond OH, NH, or F? And this is ionic. You see the full negative interacting with the full positive. All right, let's go to page 6 here for a moment. Since this hydrogen bonding is so important, I thought I'd just go over this with you one more time. So you can just relax and watch along with me. Okay, just watch along with me. This is hydrogen bonding. It's a very strong attraction. Okay, so here we have water with water, H2O. Okay, so just watch with me here. Okay, we have O, hydrogen bond, HO from the second molecule. OHO, hydrogen bond. Okay, this is ammonia. NH3 stands for ammonia. NH3 is ammonia. Okay, so watch here. Nitrogen, hydrogen bond, HN. NHN. Okay, that's the hydrogen bond between two ammonias. Here's water and ammonia. Okay, see this oxygen, hydrogen bond, HN. OHN. Hydrogen bond. How about an ammonia with hydrogen fluoride or hydrofluoric acid? Okay. N, hydrogen bond, HF. NHF. Okay. How about this one here? FHN. F, hydrogen bond, HN. Okay. Do you kind of see a pattern or some tendency in this hydrogen bond, at least a tendency? Okay, ammonia and water, NH3 and water, H2O. N, hydrogen bond, HO. N, hydrogen bond, HO. Like this can happen all throughout three-dimensional space. This is a very strong attraction. This gives it a higher boiling point. It takes a lot of energy to break these hydrogen bonds apart. All right, so once again, OHO, NHN, OHN, NHF, okay, FHN, NHO. Between two molecules. They can be the same molecules, or they can be two different molecules. Okay. The hydrogen bond. It's polar, but it's a special type of polar. Okay, it's polar. Uh-oh. Why did you do that? They blur on me? How long has this been blurry? Huh? Say that again? I can't hear.
Depends on your impact.
Oh yeah, it depends how I heart. Yeah, right. Uh-huh. I may have been lecturing on a blurry screen nobody can see. But that's okay, that's like my vision nowadays. That's how I see you guys. Hydrogen bond is polar, but it's a special type of polar. Okay, it's a special dipole. Okay, special type. Okay, let's do some example problems here. Let's do some example problems before we head on out for our weekend. All right, hydrogen bonding with water, okay? You can see a network of hydrogen bonding. Okay. So to melt ice, you need 6,000 joules per 1 mole of water. Per 1 mole. Where do you think all that energy is going? Okay, to melt ice. Okay, and all this network of hydrogen bonding. Where's all that energy going? To break the hydrogen bonds. Okay, so in order to melt 1 mole of ice, which is 18 grams, 1 mole of water is about 18 grams of water. Okay, to put in 6 kilojoules or 6,000 joules of energy, all of that is going to break apart or to disrupt those hydrogen bonds. Okay, so that's the hydrogen bonding network in water. It takes a lot of energy. What is that energy being devoted to? To break these hydrogen bonds. Yes, okay, it's a strong attractive force. It's a very strong attractive force. All right, so which of the following species are capable of hydrogen bonding amongst themselves, okay, with itself? Okay, can you hydrogen bond with itself? Okay, what do you think about H2S? Yes or no? Can it hydrogen bond with itself? No. Okay. No. What do you think the IMF or intermolecular force for hydrogen sulfide H2S is? What would it be? Dipole, dipole. Okay, what about C6H6? Okay, this is called benzene. Have you heard of benzene, or did you talk about it a little bit in Chem 1? Yeah, I did a little bit. I don't think many of my students remembered, but benzene, okay? Carbon, 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 alternating double bonds. What do you think? Okay, it's definitely dispersion, but can it, well, if it's dispersion, can it hydrogen bond? There's no hydrogen bonding, yes. Okay, that's correct. And what about CH3OH? This can hydrogen bond. Okay, what functional group is this molecule? Functional group. This is an alcohol by virtue of that OH. What's the name of this specific alcohol? Do you know off the top of your head? Okay, this is methanol. Methanol, also known as wood alcohol. Methanol. And for this question, the answer is cannot. It can hydrogen bond. I'm so sorry. It can hydrogen bond. Okay, this can hydrogen bond. All right. How about hydrogen bonding with water? Okay. Now we're not talking about an IMF with itself, but an IMF with another molecule. Usually water is generally a solvent, so we're talking about an IMF with a solvent. So how about dimethyl ether with water? What do you think? Okay, what functional group is it? It's an ether. But the question here is, can it hydrogen bond with water? What do you think, yes or no? Okay, we have an oxygen here pulling. That makes this carbon partial positive, this carbon partial positive with water. Okay, what about water? Okay, we have a partial negative. Water also has a partial negative and a partial positive. And I can see here this partial negative of the oxygen forming an attraction with the partial positive of this hydrogen. What do you think? Do you think this can hydrogen bond? Yes. Okay. See here, OHO. Okay. So this can hydrogen bond. Okay, this partial negative can interact with this partial positive, OHO. Okay, so the answer to this is yes. It can hydrogen bond with water. Okay, so it can hydrogen bond with water. Let's go to part B here. Methane, which is an alkane, can this hydrogen bond with water? Okay, the answer here is no. Okay, this is an alkane, this is dispersion, and there's no NH, OH, or F. Okay, so no. Okay, how about part C, fluorine? Can this hydrogen bond with water? There's a fluorine there, but can it hydrogen bond with water? Okay, let's draw the Lewis structure. Fluorine is forming a bond with another fluorine. What do you guys think now? Okay. All right, fluorine can pull this way, making that partial negative. What about the other fluorine? Okay, it's pulling the opposite direction. So this fluorine pulls to the left, that fluorine pulls to the right. They cancel each other out. I feel like, or I see that there's some symmetry within the molecule. So this would be polar or nonpolar? Nonpolar. So that would have, fluorine would be dispersion. Question is, can it hydrogen bond with water? The answer is no. Okay, very good. So it's a nonpolar molecule. Water is polar. There's no interaction whatsoever. All right, how about part D here? Okay, this is a carboxylic acid known as formic acid. Okay, this is not something you need to know, the name. But can it hydrogen bond with water? Yes. Okay, this can hydrogen bond with water. Okay, by virtue of that OH. Right, and then finally part E. Okay, sodium ion. Can this hydrogen bond with water? Yes or no? Sodium ion? No. Okay, no is the answer. What's the main force? What's the main interaction with sodium ion and water? Excellent, ion dipole. Okay, that's the main interaction. All right, so it cannot hydrogen bond, but the main interaction here is ion dipole. All right, nice job there. And so let's go to something a little bit new, a new topic within this chapter. This is something I just want you to know for the exam. It's a good short answer question here. Properties of liquids. Okay, all liquids will have this. Okay, whether it's blood, whether it's water, whether it is any type of liquid you can imagine. Okay, coffee, orange juice, biological or non-biological, engineering liquid, non-engineering liquid, all liquids will have these three properties. Okay, so it's a good short answer question for the exam. Okay, so all liquids will have surface tension. Okay, all liquids will have surface tension, regardless. If you see a liquid, regardless of its identity, it will have surface tension. Okay, so what is surface tension? Okay, it's a slightly stronger IMF at the air-liquid interface. So let's say this is the air, and this is the bulk liquid. Okay, right at this interface, you have just a little bit stronger IMF. Okay, you have a little bit stronger hydrogen bonding if this is water, a little bit stronger dipole-dipole if this liquid is polar. Have a little bit whatever it may be, it's stronger. Okay, right at the air-water or air-liquid interface, I should say. At the interface, you have a slightly stronger IMF, so that's called surface tension. Okay, and this is important in the lung. I actually studied this for my PhD, lung surface tension in premature infants who don't have lung surfactant. So that was many years ago, almost almost 17 years ago, so 15, 16, yeah. It was a long time ago, okay? So, your lung, the alveoli, is like a small grape. So there's the air, and then there's a liquid, okay? So there's surface tension in there that allows the alveoli to compand and extract, kind of like blowing up a tiny, tiny, tiny balloon. Okay, there's a coating that minimizes this surface tension, and premature infants don't have that. So what happens here is that anytime you have a liquid right on the surface between the air, okay, that phase, and the liquid phase, this surface that's touching that air will have stronger intermolecular forces. Okay. And that is called surface tension. Okay, so the air-liquid interface we have slightly stronger intermolecular forces. Okay, so that's the first property of liquids that I'd like for you to know. Okay, the second property of liquids is viscosity. Okay, this is resistance to flow. Okay, and the third property of liquids is actually adhesion and cohesion. Okay, adhesion and cohesion. Another property of liquids. So cohesion is the intermolecular attraction between like molecules. Okay, so that's this. Okay, have you heard of meniscus? Okay, when you measure things in Gen Chem 1, we always measure things based on the meniscus. Okay, that is due to cohesion. Okay, adhesion, an attraction between unlike molecules. Okay, have you heard of capillary action? How many of you have taken glucose blood draw? Okay, they prick it and then you put it on the strip. What happens to the blood? Sucks up, like this. Okay, that's capillary action and that's adhesion. Liquids do this. Okay, blood does it better than others. Water can do it. Okay, whatever liquid you're talking about, you know, it has some form of adhesion and some form of cohesion. Okay, so just know these for the test. Okay, just know these, like a short answer sort of thing. And then finally, all liquids have viscosity. Okay, which is a resistance to flow. And the final thing I'll mention here in this, with regards to viscosity, if you have more OH groups, it's more viscous. Excuse me. Okay, what is viscous? Okay, resistance to flow. So does it flow like water? Or does it flow like maple syrup? Or does it flow like glycerol? Have you heard of glycerol that you can buy at Walmart or the pharmacy? Or does it flow like antifreeze? Okay, does it flow like molasses? Okay, so the more OH groups there is, the more viscous it will be. Why do you think that is? Oh, something's going on with my throat.
More bonds.
More hydrogen bonding. More hydrogen bonding, more viscous. Glycerol is a very good example of this. Okay. Okay, let me give you the structure of glycerol. It's a very viscous substance, okay? It flows like molasses. Right, so on an exam, which is the most viscous substance? Okay, what are you looking for? What group are you looking for? You're looking for OH groups. The more OH groups they are, the more hydrogen bonding across the molecules it can be, and the more viscous it can be. All right? So know those 3 or 4 for the exam as a short answer, and I'll see you all Wednesday. Monday's a holiday.